All right, we're recording. You got your water?
I do have my water.
Gotta stay
It's
hydrated.
actually these are fun. It's fun to watch the water like clear. I don't know if you can tell the resolution might not be great, but in the apartment that I'm in now, the water comes out very like cloudy, but it's because there's bubbles in it. And then the bubbles, like the pattern of the bubbles, it like clears from the bottom up. It's really cool.
Ooh.
So don't be afraid if your water comes out kind of cloudy. It might just be the bubbles. Fret not.
Fret not. I have one of those Britas in my fridge that I fill up every day.
Oh yeah.
All right, we are recording. We are live. No, we're not live. This is video on demand. But we're looking at the final topic of our log unit. It's been a pretty quick unit, actually. Only 5 lessons. They kind of flown by. But yeah, the logistic curve. It's like a combination of both exponential and log graphs at the same time. We're gonna make more sense of it though. It's like increasing and decreasing. There's weird stuff happening. Not decreasing, but increasing, and then at some point it starts to level off. To get our logistic curve.
Wait, so it's bounded?
It is bounded above and below. It is legitimately bounded for the first time.
Wild.
Dealing with bounded above, bounded below. Finally, something bounded. But before we get to the logistic curve, because we want to come up with a logistic curve on our own. We want to just be able to look at it and know why it looks the way it looks. We have a famous curve here. The one on the right is the famous curve. I guess the one on the left is also famous. It's a quadratic.
What are you talking about, Mr. Kirk? There's nothing being shared.
Oh, I did it again. How about now?
There it is. I should have grabbed you.
Oh,
missed opportunity.
What's the date?
Today.
Today?
It's bound to be today.
Oh, it's bound. I don't know. The period is bounded above, or bounded below and above by 8, or by 9, by 10. Anyways, we are getting off to a really slow start. We are going to graph x squared plus 1, and then we're going to use that to graph 1 over x squared plus 1. That one on the right has a name. Some of you may know it based on journal entries. We'll get to that in a second. But the technique that's going to be used here is going to help us understand what that thing looks like, where A, B, and C are all real numbers. So with that said, and in the case of what we graph here, all positive real numbers. With that said, let's graph x squared plus 1.
Can I just start dropping points on?
Yeah, just start dropping points.
And then, bam.
Boom. All right, let's draw a curve through that.
Oh, this is a pretty bad curve. That's okay.
I'm like excited. That's perfectly fine.
Yeah, because I double back on the left side.
Plus, the expectations for graphs right now in virtual world is not as high as it normally is. All right, so we have this graph. And there's something really important about this graph that's going to affect the reciprocal in a special way.
It's always positive.
It's always positive. What's the problem? I wouldn't say problem. What happens when we have a graph that is 0 when we take its reciprocal?
Like when we're trying to take the reciprocal of 0, that doesn't exist.
Exactly. But this is going to exist everywhere, right?
Nice. So the domain for the function and its reciprocal is all real numbers. Nice.
So let's reciprocate this thing. A reciprocal of 1 is 1. Reciprocal of 2 is 1/2. Reciprocal of that looks like 1, 2, 3. I think you messed up. Well, no, you shifted up 1. I messed up. It's a 5. So 1/5.
Okay.
All right. Okay. I was anticipating 4, but I forgot we shifted it up 1. Okay. All right, and then the graph is going to look like this.
This is so exciting. Oh wait,
riveting.
It glitched out. Okay.
Boom.
Cool.
Like mountain. So, do you know the name of this graph?
Hobbiton.
Hobbiton? For our Lord of the Ring fans out there, this is one of the graph of the form the Witch of Ignessi. So some of you have written about this mathematician. If you haven't, there's a person you can look up, research, find out what makes them so great. But this is a curve that they're Maria Ignessi. This is a curve that they concerned that was something that they worked with a lot in their career. And the beautiful thing about this is that it has a domain of all real numbers. It is the reciprocal of a graph that is always positive. Some fun facts about this graph. There's a finite amount of area under it.
What? But it goes on forever.
It goes on forever, but there's a finite amount of area. Meaning it never gets past a finite number. So it's infinitely long, but the area never gets past a finite number, a specific finite number. I can't remember what it is. I think it might be like 2 or something like that. 2 units.
2 sounds good.
So let's pretend like that is. But just some cool things about this graph. Look it up. Have fun with that. So the Witch of Ignessi. We're going to use this technique, though, reciprocating something always positive to understand this curve here, the logistic curve. Useful curve that we'll talk about later. But Mr. Contreras, I have a challenge for you.
Oh, no.
Given A, B, and C, all positive real numbers, can you graph that thing? Or can you graph what it looks like, given A, B, and C?
I'm just going to say yes.
Awesome. The optimism is necessary.
Well, yeah, I think so. Because, well, like, let's break this down, right? We have e to the negative b x power. So that's an exponential decay, right? So we have something that goes like that. And then we're going to have a scale. We're going to have a vertical dilation by terms of a, and then a shift. And then we're going to reciprocate. And then there we go. We're gonna have something totally graphable, just purely based on the transformations and the reciprocator thing that we knew from before.
And I think if any of you out there are particularly visual people, you might even be able to like see this graph in your mind right now. This, and then you stretch, and then you shift up, you reciprocate. I can kind of see it in my mind. Now I've seen it before, so that might be an advantage that I have that you all don't have. But it's definitely something that we can work our way towards and kind of understand the common properties, like how big is it, what's its what is it bounded by. So let's do it. E to the x. Let's just do each of these transformations really tiny. E to the x looks like this. What is its y-intercept?
1.
1. So I'm gonna actually write the coordinate 0, 1.
The happy point, or the all reliable.
All reliable. All right. What was that first transformation you said we did to it?
We have to reflect it across the y-axis because we have a negative e to the negative b x, and we know that b is positive, so that we know the reflection is going to happen, and there is going to be some sort of horizontal dilation happening.
But that all reliable stays there. Cool. So this is e to the x. This is e to the negative bx with some number, positive number b. We have that reflection. What's the next thing that happens?
We got to dilate in the vertical direction.
So this is actually going to affect all reliable, right?
Yeah, it is, right? Because we're going to have, whenever we plug in 0, we're going to get just a.
So instead of 0, 1, now it's 0, a, whatever that real number, positive real number a is. All right, this is a e to the negative bx, given a and b positive. Keeping all reliable in our minds.
All reliable.
What's the next?
Vertical translation by 1. So our new y-intercept is a plus 1.
So 0, a plus 1. And something else is now, well, everything else has now changed, but something else that we care about in exponentials has changed. Yep, that asymptote.
Horizontal asymptote.
Because now we have a horizontal asymptote at y, not y. Oh, yes, y. Y equals 1.
Yep.
Cool. And I haven't actually graphed this exponential yet. Decay. There we go. What happens next?
Reciprocator.
All right. Okay, so we get to think about this. We have to think about this. This one will be a little bit bigger. What can we easily reciprocate?
Overliable.
Overliable. So that becomes 0, comma
1 over a plus 1.
0, comma 1 over a plus 1. All right. And there's one other thing that's easy to reciprocate here. If you think back to the reciprocal rules.
1.
1, right? Anything that is 1 stays where it is. What is 1 in this graph?
Our horizontal asymptote is 1.
Yeah.
So our horizontal asymptote shifts up to just above where that is.
So I've kind of zoomed in here. We have y equals 1. Why have I put the asymptote right at the top?
Because that's going to be our upper bound now. Because when we're reciprocating things that are approaching 1 from above, then the reciprocal of that is going to approach 1 from below.
1 over number, yep.
Like 1.001, right? That's a number that's slightly above 1. So if you take the reciprocal of that, you're going to get a number that is slightly below 1. So you're approaching 1 from below.
Sweet. So as we go out to infinity, we were approaching from above. You've just told me that we're approaching from below now. Cool. And how about the other side of this graph?
Well, we
I'm actually going to be
know
annoying here.
our end behavior. Oh, you're just moving it. Okay.
Yeah,
our end behavior to the left, as x approaches negative infinity of our previous graph, our function goes to infinity. And the reciprocal of going to infinity, like the reciprocal of infinity, is we're gonna approach 0, I guess, from above. So we're gonna have a horizontal asymptote again at 0.
Yeah. So we went from having 1 asymptote now to 2 asymptotes. Because we're never going to get both. Yeah. Double asymptote all the way across the sky. Speaking of old things that we experienced when we were younger. Double rainbow all the way. Anyways. All right, so we're going along. And then we need to get from here to here. So I think we just need a smooth curve along the way, right?
I think so.
So we're going up.
But then we need to smooth out to level off. Huh.
Boom.
Interesting.
That. And do I have any more room? Well, so we're almost done.
Yeah, because we need to also do a vertical dilation.
Yeah, we forgot about that vertical. Oh, I forgot about that vertical dilation. Let me go ahead and do the last one in red. This is our function. C divided by 1 plus AE to the negative BX. That's a logistic curve. We have our horizontal asymptote at y equals 0. That doesn't get affected by a vertical dilation. What does get affected by a vertical dilation here?
Overliable.
Overliable does. So it's going to go from 1 over a plus 1 to c over a plus 1, right? 0, comma, c over a plus 1, or 1 plus a. And then the upper bound also gets stretched?
Yeah, our y equals 1 is going to be y equals c instead.
And then we are still approaching 0 on the left, and now we're approaching C on the right. This is our logistic curve. Awesome. Why does this curve find its way into the exponential logarithm unit?
Because there's an exponent in it.
Oh, yeah, true. I guess what I was trying to get at was we've been modeling things for a couple weeks now. Exponential growth, exponential decay. There's a problem with exponential growth, though.
It's not like feasible.
Yeah, right? Like if you have $100 and you get 6% interest,
60% interest. That's what's up.
Yeah, because 60% interest every year. How much money are you gonna have after like 100 years?
A lot more.
1.06 to the 100. Actually, that's not that bad. That's $33,000. I guess it's not unrealistic. But there's no bound to this amount. My example was a faulty example. There's no bound to this, but there is a finite amount of money in the world, I guess, unless like it's all digital and money doesn't really exist.
Oh my gosh. We're gonna go down so many rabbit trails.
I know we are. Speaking of rabbits, those things like rabbits reproduce, but they don't reproduce forever. There's a population maximum, right? There's the environment of which they live in has a sustainable amount of, or a finite amount of resources to sustain those rabbits. You can't have an infinite number of rabbits. Although that might be cool. We've been talking
that
about,
sounds crazy. But
Yeah,
there's like, have you seen that video of like the rabbits in Japan where
no.
there's like an island of feral rabbits and you can like feed them, but it's just like masses of rabbits. It's crazy.
God.
But thinking about that, like that is, I think, the most rabbits that could live on that island because there's no predators there, but there's still a finite amount of resources like food and places to sleep, those and water. Those are all things that are limiting what the population of rabbits is.
Another one is like bacteria growth. Like if you have a petri dish and you have like one bacteria and then I forget the name of it, but when it splits into two,
Splicing?
I can't remember, but then and it grows and grows and grows, but there's a finite amount of space. So like exponential models are great only to some degree. We need something that models it a little bit better. And I think that this graph right here might do a good job. You start out small, you start to increase. If you're thinking about rabbits, there's a point at which the rabbits can reproduce the fastest. But then at some point, the resources start to take effect and it starts to level off and you peak at whatever that population max is. So the logistic curve is almost a more realistic exponential model. That's why it's also making its way because, like you said, there's an exponential right here. But we're also able to model things a little bit better with logistic curves, I think.
There's a lot more applications for this.
All the things we just said are in that text right there. Compared to exponential functions, the logistic function gives a better model for certain types of growth. These functions, like exponential functions, increase quickly at first, but due to restrictions that limit the size of the maximum value, eventually the rate increase slows. It's always increasing, but it slows and then it levels off. And theoretically, it's always increasing, but in reality, things are discrete. So at some point, it's going to stop. But yeah, what do we got? We got bunnies. Some examples of bunny populations.
Crab populations.
Crab populations. So populations. What else did we say? Bacteria growth.
Bacteria. I think there's things with like medicine, with like if you're going down and like the absorption of a medicine, so the amount of medicine that's in the system.
Medicine in the system. My favorite one is linguistics.
What do you mean by that, Mr. Craig?
It's like linguistics. That's the study of words, right? I guess that would be etymology. But linguistics is the study of words for all intents and purposes. But like you start like every year there's a new word that's super popular. I don't know, what is it right now?
You're on mute.
That's not what I mean, but that is a thing that's said more and more and more.
Oh, but like truthiness, right? That was like the word of the year.
Truthy,
like became a thing.
Yeah.
Lit.
We still say lit in marching band. That we say pit is lit. Pit is the group in front of the band. Pit is lit. What was it for us when we were in high school? Like bet. I tried to start a word. Ripping. That's ripping, but it never caught on. So my logistic curve would be like, But the spread of words, so that like one person comes up with a word or starts saying the word, and then it becomes the next TikTok sensation. But then eventually, everyone but you and I knows the word, right?
But then the students tell us like about vibes.
Yeah, yeah,
I didn't know
exactly.
about vibes. Now I do.
Linguistics that behaves logistically. Rumors behave logistically. Someone spreads a rumor. Hopefully, it's a positive rumor, like Mrs. Contreras, you're awesome.
Is that a rumor or a fact?
Rumors can be true, but someone starts a rumor, it spreads really fast because more and more people have it, but eventually it kind of dies out.
Or even just news, right? Like the way that news is spread, if it's disseminated through, like a crowd rather than, like disseminated from a central news source.
There's a finite amount of people that can know the news.
Mm-hmm.
There's still lots of things. I don't think I have. I guess I could write down rumors. I don't know how to spell rumors. I think it's that. I don't know. This is why I'm a math teacher. Classic math teacher joke. In the back. Okay, so things behave logistically much more often than they do exponential. Exponentials are good, but they do have limiting factors. All right. Some more stuff about logistics.
Wait, that was a really funny statement because logistic functions have the limit, but then the exponentials have limiting factors, but there's no actual limit, and that was funny. Okay. Actual math teacher jokes.
Totally intentional. All right. So we got some basics down. There's one last thing we want to share with you guys, and this is kind of lame. I don't like to do this, but there is a idea about logistics that's useful to know, and its proof requires calculus. It requires to be able to understand the rate of change of a curve that is not like a line. So you'll get that later, but there is something called a point of inflection. Mrs. Contreras, you teach BC Calc. What is a point of inflection?
A point of inflection, endearingly referred to as POI or POI, is not to be confused with poi, the food, which is mashed up taro that's steamed, and it's not super tasty, but if you eat it with other things, it's better. Or fire poi, which is a type of juggling that involves things that are on fire on strings, and then you just like swing them around. Not to be confused with those, but those are fun. And look those up if you want to. Point of inflection is where you're looking at a change in the concavity. So you're looking at how, if something is like, the curve can be described as something that's like a spoon that's facing down, changing to a spoon that's facing up, or vice versa. If you're like, wait, my hand thing. So like where my thumbs are intersecting is a change in concavity, and that is what a point of inflection is. The rate of change is changing. The sign of that. That was poorly explained. I really want derivatives.
Yeah. There's a lot of terms that we can't really talk about in an educated way right now because there's a lot of stuff that happens before it. But we're increasing, and we're always increasing, but we're like the amount that we're increasing is increasing. That's what you mean by that, like a second rate of change, the rate of change of the rate of change?
Yeah.
Some points at some point it must start to taper off. Where's that point that it starts to taper off? That's the point of inflection. And the thing that we're not going to explain to you, I was going to ask, do you have the spoon?
I do have a spoon. I always keep a spoon nearby me when I'm teaching calculus. So this spot right here, that's the change in the slopiness, right? That the slope on this side is like facing up, and then like this part is facing down. And then if you turn it over, it's still going to be point of inflection where the spooniness is changing. Slopiness, yes.
Change in spooniness. All right, so with that said, the thing that we're not going to justify is not what a point of inflection is. We've now justified what a point of inflection is, but it's the fact that this point of inflection in a logistic graph happens directly between the lower bound and the upper bound. So in the case of this graph, the lower bound is 0, y equals 0. The upper bound is, what did we say it was? Let's go ahead and say C.
C, yeah.
Okay. This point happens at some value, comma, C divided by 2. The point at which we are growing the fastest is when we have half our population max, which kind of makes sense, I think.
because that's when you start, I guess, like running out of resources.
Mm-hmm. But you have the most amount of
Momentum.
Momentum, yeah. All right. Anyways, proceeding. We have been given the fact that that point of inflection is halfway between the max and the upper and lower bound. Where is that question mark? What is the x coordinate? The point of inflection has a y coordinate halfway between its asymptotes. Logistic functions are always bounded above by y equals c and bounded below by y equals 0 unless there is a vertical shift. Find the coordinate of the point of inflection. X, comma c over 2. What is x?
Well, can we just plug in c over 2 to our original and then try to solve it?
Yeah. So the original was, do you remember what the graph is?
C function? Over 1 plus a times e to the negative bx.
Awesome. And we want to know that x value that makes the output c divided by 2. All right. Let's solve this thing.
Can we take those c's away?
Yeah, we can take this. I was going to say to the viewer, pause. Try to solve this on your own. Good exercise in solving logistic equations. But yeah, let's go ahead and start in 3, 2, 1. Let's get rid of those c's. 1/2 of. Wait, can I do the next step? Just because it's my wrestler name.
Sure.
I'm gonna reciprocate both sides, and since this is not an inequality, I can leave that equal sign. I don't have to switch anything. 2, 1 plus a e to the negative bx. It's valid to reciprocate the sides of an equation.
Mm-hmm.
Good stuff. Good stuff.
We can take away 1.
Take away 1. And then that's nice.
1 equals, yeah.
Okay.
Divide by a.
Divide by a. Oh wait, can I do something? So the right hand side, right? That's just 1 over e to the bx, right?
Uh-huh.
Reciprocate. I'm gonna reciprocate again. Okay. Take me home.
Well, we have e raised to the bx power. We want x to come out of the exponent. So we need to take natural log of both sides and then divide by b. So we get natural log of a equals bx, divide by b.
Oh, but
yeah.
Your choice of logarithm gets rid of the e. ln e of e.
Mm-hmm.
Nice. And you divide it by b?
Divide by b, and then we get what we wanted. Yay.
There we go. There it is. So the point of inflection is entirely dependent on a, b, and c. Those numbers given to you in the function. The point of inflection, the poi. I'm a fan of that new vocabulary. I've never called it poi before, but now I'm going to.
It's just because poi is fun to talk about.
We had someone at STEM Arts Night last year do poi spinning.
Oh,
not
wow.
with fire.
Okay. Glow sticks?
Yeah, glow sticks. But it was pretty sweet. And then c over 2. There is your point of inflection. The point at which this graph is growing the fastest. Let's apply it. Let's
use what?
To an excellently designed DuckTales themed word problem. So we've been saying constantly that this is a good model for things that grow exponentially that also have some sort of carrying capacity. So with your best not Donald Duck voice, with your best thespian voice, can you read to us our word problem here?
There are 6,000 employees at Waddle, the company owned by Mark Beeks in Duckburg. Woo! One employee returned to work after taking vacation with the bird flu.
That's funny because these are all birds.
Yes. But it's not that the employee is taking vacation with the bird flu. The employee is contracting bird flu while on vacation.
Mm-hmm, mm-hmm.
Yeah. Okay. All right. The spread of the virus is modeled by the equation below, where I is the number of infected employees and T is the time in days. Mark Beeks will close the building when 25% of his employees are infected.
That's a evil like boss. I feel like
Yeah,
if there's bird flu is spreading throughout amongst avian type characters, particularly, I feel like he should probably close down immediately, and then just
yeah.
have everyone work at home.
Especially because it's a tech company, like everyone can work from home.
Exactly, right? What does Waddle do? It's a tech company?
Yeah, they do things like I think it's supposed to be a play on Facebook, like combined with something else.
Okay. Well, it's a bird pun. Waddle waddle do do do
Wow,
do.
wow. Got
All
any
right.
grapes?
So we've been given here a function. Um, the 6,000 kind of makes sense, right? In the
Yeah, six
numerator.
thousand is the carrying capacity, or like the upper limit, because 6,000 is just the number of employees that are in that building.
And then there's these other numbers that were probably just established using prior data from the spread of viruses.
Mm-hmm.
So those numbers are coming from something. But in this example, we don't know what those numbers are. It's using prior data. All right, we'll do some problems later that don't give us any prior data. We'll have to find A, B, and C given it some information. But here, we're given the function. That's kind of nice. All right, sketch a graph of the function.
Okay.
Am I about to scroll down and see a crab? No,
No.
I'm not. I was nervous there. Anyways, we need to graph this thing.
Well, we know that C is 6,000, right?
Mm-hmm.
Because just from reading off of our model, 6,000 is C. We also know that A is what? 5,999. And B is 0.8. So from that, we can plot our old reliable.
Or reliable. That's C over 1 plus A, right?
Mm-hmm.
And if you forget that it's C over 1 plus A, that's totally reasonable. Just plug in 0.
Just plug in 0.
You get 5,999 plus 1. So 6,000 divided by 1 plus 5,999. Oh, that's easy. It's almost as if we chose these numbers intentionally to make algebra easy. That's going to be 1, right?
Yes.
Cool.
Because that makes sense. There's one employee in the beginning who has the virus, the bird flu. And then
perfect. So this is time. This is time 0. Okay.
And then we can plot our POI.
Our point of inflection. So we'll ln A over B, comma C divided by 2. So this is my scale is clearly not very good, but I'm going to live with it.
It's okay. It's a sketch.
Yeah. So what is ln A over B divided by 2? I got a calculator. ln of 5,999. I said one too many nines, but I did not type that one too many nines. Divided by B, 0.8. So I just noticed something. You wrote 0.8, but I see a negative 0.8 in the problem. Can you talk to me about that?
Well, in our original that we were like the very first thing that we were doing when we were finding our logistic function curve from just looking at like transformations, we had a negative before the B. And so I just remembered that, and then I took away the negative from my exponent. So that B is going to be positive.
Sweet. I feel like that's a common mistake, which might solve people's problems. If you get a negative number as your answer, then it's probably wrong. Time should not be negative. Unless, of course, you're looking in the past. We're looking in the future. At what point will it be 3,000? It starts at 1 and 0. So my answer was 10.874. So I'm going to go ahead and round 10.8741. I'm going to round to the closest 1,000. So 10.874. 10.874 is when I'm at 3,000. This is ln A over B, comma C divided by 2. 10.874, comma 3,000. Sweet. And I think that's like kind of good enough for a sketch, right?
Yeah, we need to connect them. Like we can just leave the points. But yeah, that looks good.
Yeah, my favorite thing was when you ask someone to draw a circle and they draw these 4 points, but then they forget to draw the circle. Makes me sad. That happened a lot to me when I teach geometry. Anyways, we are here. We have a sketch. Cool. How many employees are infected after 5 days?
I think we need to plug in 5.
So f of, or I of 5. Let's use a correct. I of 5 is equal to 6,000 divided by 1 plus 5999 times e to the negative 0.8 times 5. Are you Desmosing it?
I'm trying to.
Sweet, sweet, sweet. I'll give you a chance to do that.
I need to change my scale because it looks very exponential right now. That's not the goal. It's because I need to have my upper bound is like above 6,000.
Are you sketching the graph in Desmos?
Yeah.
Sweet.
Let me see. Wait, how can I share this with you?
I can stop my share.
Oh, true.
Boom.
Is this the dancing for waiting?
I wasn't sure if you could see me. I thought you were looking at Desmos. Darn.
So we have, this is
Nice.
the graph.
Can you zoom out for me? So that's way sharper than my graph, but mine's a sketch. So it spreads fast, as viruses do.
As viruses do. And then we're evaluating at 5?
Yep, 54.115. And that's 54.115 people, right?
People.
So I feel like that the answer should be 55.
Ducks. 55
Ducks.
Birds? Birds.
Yeah, duck's a bird. Because, and I think she's 55. I guess this is a philosophical question, but if you are 0.115% sick, if you are 11.5% sick, I feel like you're sick.
Yeah.
Yeah, so 55 birds. But whatever. All right, that's B. That's how many people are infected. That's the power of this function. But it's giving us a more accurate understanding of the spread of this virus rather than an exponential one that would just shoot up.
Mm-hmm.
At what time is the virus spreading the fastest?
Well, didn't we say earlier that that's where our point of inflection is?
It's the point of inflection. That's when there's 3,000 people sick. There are 3,000 people spreading, and there are 3,000 people to still receive the spread. But as we get past that 3,000, there's less people to receive the spread. So, yeah, 10. What did we say the inflection point was? 10.874. So the POI at day 10.874.
Oh wait, should I stop sharing and then switch to you?
Oh yeah, I've been writing. Sorry.
All right, there you go.
Boom.
Oh, and then it just showed up on mine.
Sweet. Here we are. 10.874. That point of inflection is when this is spreading the fastest.
Cool.
And then this is the most annoying one. How many days will it take before the building is closed? So the building closes at 25% its capacity?
Yeah, when there's 25% of the people or the birds are infected.
So that's 1,500, right?
Yes, because that's 6,000 over 4.
E to the negative 0.8 t. And this is going to be a log problem. Or a natural log problem. Divide by, ooh, this is nice. Divide by 6,000 on both sides.
Mm-hmm.
And we're going to get 1/4. So maybe we could have just like gotten rid of that 6,000 and 1,500 right away. 5999 e to the negative 0.8 t.
Mm-hmm.
Reciprocate. That's how I'd imagine my personality would be if I was a wrestler. I would talk like this all the time.
Sounds
like
curiously similar to your pirate voice.
The reciprocator, the wrestler, wears pirate clothing. Just so you know. 35999 e to the negative 0.8 t. Just doing some casual math.
Casual.
What is? I don't care. 5999. I'm not going to simplify that. I'm going to be using a calculator ultimately. E to the negative 0.8t. Take the natural log of both sides. ln of 3 divided by 5999. I know that a number less than 1, the log of it, is going to be negative, which is good because I need to divide that negative number by negative 0.8 to get a positive time.
Yeah.
This number is negative.
And then dividing by again
So
negative.
And you got the answer there at the top?
Boom.
Let me erase this.
Oh, oops.
No, you're good, you're good. And getting that gives us 9.5. So what's his name?
Mark Beeks.
Mark Beeks knew for 9 days that a virus was spreading, yet declined to close down the building. Sounds evil and diabolical to me. Is the character evil in the show?
He's like not great.
He's not great.
I would say that like no one in DuckTales is like that pure of heart. Maybe Webby.
I feel like Donald Duck is pure of heart, right? He's just like...
He's got some anger issues.
No. How about the lovable doofus? What's his name?
Oh, Launchpad.
Is he pure of heart?
I guess so. But I mean, he's not really like applying himself to the best of his ability to like reach his full potential.
Okay.
Like they're all flawed characters, but that's also part of the fun.
Yeah. I feel like that's every show, you know?
Yeah.
Character's not flawed, then what's the point of developing it? There's nothing to develop. There is a quick lesson on theater and the development of characters and how all characters are flawed in some way. As you watch your next movie or you read your next book, think about that.
Or as you watch the next math video.
Yeah, find our flaws. All right. I'm going to stop my my share. Any words of wisdom? I'm going to get another geek wisdom out here.
Oh, okay. Wow. So I feel like I need to like be ready with something. It's good to be responsible for something, even if it's something small like a plant. Yeah.
I like that. Take care of something is how I interpret that. The irony in mine is the one I turn to. It's from George Orwell. 2 and 2 make 5.
What?
That's what it says from 1984. From the book 1984. So that kind of makes sense. Misinformation. Don't believe everything you read is my word of wisdom today. But believe what we've just told you today. Logistic curves.
And think about some applications. Look into some for your journals. It'll be pretty interesting.
Alrighty, let's get out of here. Ready?
Bye.